so quite frankly, I must admit that it's an honor to be here at Vanderbilt. I actually have some history going back with the university. And in the early 80s, we had some collaborative funded work here at the university. And throughout this whole thing, we've had various programs, okay, with Vanderbilt as well, including some recent things with Sandy. And in fact, I'll Sandy Rosenthal, I might even say some things about that as we go through this. So Vanderbilt has been a part of our programs, and I hope after today's visit and talking to some people, it will be a growing part. Well, I don't know how this is going to go, so let me see here. You know, first of all, I want to tell you, everyone here, is that I own the computer, I own the hard drive, okay, and I do all my own graphics. All right, so that so you know that I don't have a big we do have a big graphics department behind us, but this stuff is all mine. So I spend a lot of time on airplanes. You get a lot of time to do this. So, you know, when Bridget came and asked me if I would come here to speak, I said, well, certainly. And then she thought for a while, and she says, you know, this is a pretty technical audience, Kaz. She said that this is not like going and speaking to the Department of Energy. So I should say, is there anyone here from the Department of Energy on the whole thing, or the CIA or anything like that? She said, you really have, you know, we have these engineering departments, and the students are pretty sophisticated and everything. So I said, okay. So last night I went out with Bridget to dinner, and I showed her the talk. So I started in and let's see if this projects. I thought that this audience probably would like something that's fairly technical. And this is it, right, Bridget? This will be good on this whole thing. Yeah. Well, it does have a point. And I'll be talking about solar photovoltaics. And the point is this, is right now, this is a hot field. Right now, there is more venture capital money coming into this technology than one can imagine. And I put this up here for two reasons, is that first of all, this has every buzzword, okay, if you want to have it. And the other thing I just want to point out that if you're starting a photovoltaic company now, to use one of these words in the title like nano, okay, that's worth immediately about $20 million of venture capital money. So that there is something behind this. In fact, if we look at this, I just would like to show this. This is what the venture capital investments have been for the last 3 or 4 years. And this is only venture capital money into the thin film technologies that I'll say a little bit about, and only in the United States. So last year there was something like near $160 million invested in this technology. To give you an idea, the photovoltaic U.S. Department of Energy's budget was about $132 million on the whole thing. And this year so far, okay, it's approaching. I heard the other day there was a company that got about another $75 million. So now in the thin films, it's probably up around $250 million of venture capital money. And this could be very, very dangerous because people remember the dot-coms and all these things that venture capitalists are not very patient with getting return on investments. And this is a technology that is not going to have a return on investment within a couple years. So there's always a danger in seeing all this money comes in. But there is another message in this whole thing for students. And that is that right now we have a real shortage of people coming in on the technology side into photovoltaics, in the whole industry. And so if anybody is thinking of this, okay, this is a real opportunity. I'll say some things about that. Well, what I'm really going to talk about, I think, is this. Is photovoltaics, okay, at the tipping point. And I'll define this in a little while, but it's a term now that so many people have already heard and everything and read books about this and everything. But truly, this technology is at that point, that critical point, that it can make a huge impact, okay, in the energy sector. And this is really what I'll be addressing. Well, after I started off with Bridget last night and I showed her these very nice slides, okay, Bridget told me this was very nice and it's a nice, serious beginning. She said, but I told you that this is a sophisticated audience. Am I not right? And that you know, they get a hell of a lot of PowerPoint presentations around here. And you know, the faculty's kids, and grandchildren do PowerPoint presentations better than this, is what Bridget told me. Okay. She was only being supportive, okay, on this whole thing. So I think what she was indicating, well, before I go on, let me just say that when I go through this talk, there are 4 messages, because it's very difficult for me to stop and say this is my message, but so I have 4 of them. The first one I'm going to give is that solar is real, okay, in the future and now, all right? It's not something that is just a future technology. It's a real business now. It's about an $18 billion business worldwide. The second one, that there's an investment in policy and R&D are equal priorities. One without the other won't make this technology go. Third is that there's a drastic need to drastically shorten the time from research bench discovery to use by the industry, something that we don't do very well, and you'll see all those things as we go through this. And finally, there's a huge need for paying some attention to science and technology workforce. Okay, the people coming out of the universities, whether it's undergraduates or graduates, there's a huge need in this technology on the workforce side. So anyway, you know, if you get old enough, your students will find this out, that every year you come up to an anniversary of something. And now this technology is kind of a little bit more than 50 years old in its modern phase. And I should point out that this technology, you know, actually had its very, very first beginnings back in the 1830s. And photovoltaics was actually invented, okay, or discovered, really, by chemists. It was our token chemist, okay, in photovoltaics. You have to have one on this whole thing. So it was Becquerel who was working in the laboratory using electrolytes and solids and dipping these electrolytes and these solids into the electrolytes and looking at different effects that were happening, mainly to see what the effect of materials had on voltages and currents that they had. And actually, he didn't do this at all. It was actually, as all your students know, it was a graduate student who was doing this, okay? And the graduate student actually came back to Becquerel and said, you know, Professor, that when I was doing these experiments, he says, you know, during the day, the results are different than at night. And he said that somehow the light is interfering with all these results that we're having. And of course, like any good professor, okay, Becquerel said, well, why don't you just close the blinds? However, right? But the student was smarter than that. He kind of saw the relationship between the intensity of the light, okay, and the currents that were coming out of this thing. And in fact, by doing this and brought this back to Becquerel, okay, gave the evidence for the photovoltaic effect. Of course, the interesting part is no one can ever give me the name of that graduate student, right? So next time you see your professor, okay, in the laboratory, your dissertation working on it, just remember, okay, that your name is first on the publication, not second on the whole thing. So, all right, that's my whole thing on the photovoltaic effect. But once again, in the 50s was the big thing coming up with the PV effect, and it was work from Bell Laboratories. And so in 1953, 1954, the stuff started up. And then the first that was kind of a tipping point. And then the first point after that, there was a demarcation, came in when we started to see stuff happening with satellites in space. How many people here were born before 1958? That's good. Yeah. You're not alone. Not alone. Yeah. This is good. There are at least 6 of us here on the whole thing. So, and I'm going to say something about what happened, okay, at this point. What happened to science and technology education and interest as a result. So, anyway, so I went back last night because Bridget told me that this opening wasn't good enough. And so I did a little movie that goes back 50 years, okay, looks at this stuff, and then kind of looks ahead in this technology for the next 50 years, all right, on the whole thing. So let's see if this works. This is what you had in mind, right?
Oh, yeah.
I hope there are no lawyers here. So if there's anyone under 18, you'll also have to leave. You all know that feeling. That's a solar cell, okay? So that's about it. Are there any questions on the whole thing? Or as Bridget told me once before, as I really should get a job. I have too much spare time on my hands. So anyway, because Bridget was so good in this whole thing and pointed out, in fact, I have my own methods of finding out when we met Bridget. And I want to tell you that you're absolutely right because, as you know, Bridget is quite an athlete on the whole thing, and I do have some proof of that on the whole thing. And this was from the 2006 run in San Francisco that I was able. But I went back. I keep records of everything, and I did go back into 1989 in your first run on this whole thing. And someplace you can certainly see, if nothing else, I think Bridget, some places up here is finished okay in the running there in the women's division on the whole thing. What I was most impressed with, though, because I looked at this, is I went over and looked in about 8 years later and saw that Bridget had taken 10 minutes off of her 5K time in that thing, which I think is pretty spectacular in this whole thing. But I always tell people, boy, I have the best job in the world with this event, because where else could someone, go to the scientific conference like this, and go to this group of scientists and tell them that they have a good opportunity that you can get up on Wednesday morning and go run at 6 o'clock a.m., and get all these people out there. Not only that, They pay you to do it. All right? I mean, that just shows that there's room for anyone in doing this. Well, this is not what I was going to talk about, okay? But I want to point out, even though I'm going to talk about photovoltaics, there are other solar approaches, all right? And certainly the first ones are in the solar thermal side on the whole thing, and there's more than one approach here. I think people are probably very, very used to seeing solar thermal, where you do some solar thermal hot water systems on your house. I mean, this is an old technology that goes back quite far. But there are also solar thermal electric technologies. Sometimes these things are called concentrating solar power. And, you know, they're the things you see like this with these large arrays where you take mirrors or heliostats and focus the sun's rays. For instance, this happens to be a tower approach. This is a current system that was just commissioned in Spain. It's about, I think, 600 megawatts of power. This happens to be the old Solar 2 installation, I think, in California or something like that. And I think now it's being used as a telescope for the University of California. They actually didn't quite work out. But anyway, you can see you can focus on a central point. Or, okay, you can also have things that... I should not let everything get in the way of me here. I guess if you press the laser, I'm an electrical engineer, you won't get the slide to it. So. Also, you can have parabolic dishes to do this, or even the most common way now are also you can have parabolic troughs. And there are some very large systems in California. In fact, the biggest one operating in the world right now on the parabolic trough is about 380 megawatts right now, and they're going to expand it up to a gigawatt of power coming out of this. And so these are kind of utility scale solar projects. And these are not the ones I'm going to talk about, okay? What I'm going to talk about is solar photovoltaics. And I was warned, in fact, I think I brought some more things with. I wonder if this survived. That I might want to say something about how photovoltaics works anyway in this whole thing. So, this is a very, very funny word, photovoltaics, and it's caused a lot of problems over the year on being able to pronounce it. But I'm always happy to say that some people have been very successful at doing this lately, I think. Photovoltaic technology. So now if we have the money coming into this, we're okay in the whole thing. So, but we do have a new initiative, okay, that President Bush did put in this past year, which is for the first time, okay, it's starting to look in the renewable side and in photovoltaics in general. It looks like we have a chance here in the United States, and I'll say something about this later. But let me talk about what these photovoltaic cells are. They start off with a semiconductor, all right? And in fact, this is a book on the sun. I had to get something to see if I could carry this thing with so it wouldn't break. God, I'm successful. So this is a solar cell, okay? This is a common silicon-based solar cell. So it's made of a semiconductor, silicon, the same stuff that Mac has as far as all his electronics on here. And if we looked at it from the side, okay, and had a microscope and looked at this thing, we would find out that it actually is two layers of silicon. And they do this by diffusion, okay? For instance, in this one, they start off with a wafer that's doped with boron, and then they put phosphorus diffuses in, and they get a very thin layer on the top there. So as you can see on the side, you can see it's two layers, okay? One P-type, okay, which is positive carriers, and one N-type for negative carriers. The separation gives you a voltage. So you have somehow relating to this like in a battery, all right? It has a positive and negative. Well, the question comes is, what happens when you shine light on this thing? When you shine light on this thing, quantum mechanically, the energy from the light can be transferred, okay, and get those carriers to move inside. And as you know, when you have movement of electrons, you have a current, all right? But it can't do this unless you have some contacts, because this is nothing but a battery. In fact, it was originally called a solar battery. So you have a top contact, which is the negative contact, a bottom contact, which is the positive contact. The light comes down, and takes these carriers, okay, which are separated now, and they can move. So the separation gives you the voltage. The movement in there, okay, gives you the current. You have voltage and current, so you have power. So that's all how this very, very simple device works. It's a battery that instead of having lots of chemicals on the inside to provide you with all these things, what happens is the sun, okay, is the force behind this. So it's a simple, rather simple device, but the problem with it is if you look at it, in fact, you can see here, well, in fact, it's not even done yet, so that on the top you have to put some kind of anti-reflection coating so that the stuff, you know, if this were just silicon as it is, it's pretty reflective. So you put this coating on the front so that the light gets absorbed in there, and so you can get every photon in there to give you those carriers on this whole thing. And obviously this solar cell has a grid on the front so the light can make it to the semiconductor. So that's simply how it works, all right? Of course, if you take a class, you'll find out that isn't all quite true, and it's a little more complicated, okay? But otherwise, that's as deep as I'm going to go into any sort of physics or anything like that. Well, you know, so one of the problems we have is maybe with this word. I always thought on funding. So I thought that if we changed it and just added one more letter to it, the funding would go up on the whole thing. If we got the oil in this somehow. So does anybody in here read Arabic? No? So is my Arabic okay? Is it true? Good. I can use this, by the way, at the Department of Energy without everything. They say, oh, that's really good on the whole thing. They have no idea what I said. So you have to ask him afterwards, because I'm not going to expose myself anymore into this whole thing. So it's always been a problem with funding any of these things. In fact, it is a kind of a big confusion, because one of the big things we love in photovoltaics is the price of the barrel of oil to go up. Every time the barrel of oil goes up by $2, what does the press report? We need solar on the whole thing. But guess what? How much electricity do you think we make by oil? Almost none. If you go to the United Arab Emirates, yeah, they make almost all their electricity by oil because they have a lot of oil. Or to to Indonesia has a lot of but in the United States, about 4%, okay, most of it is backup power that comes from that. So not very, very much at all. Oil is a transportation fuel. Okay, photovoltaics makes electricity, and I'll say something about what it competes about in a few minutes. Well, going back to the beginnings, okay, these are the three inventors, okay, that solar cell, Chapin, Pearson, and Fuller, who in the middle 1950s did this whole thing. And it's very interesting that about Bell Labs and how it was operated back then, and it would be really as a model on how we should be doing things now. But in fact, right after that, very, very soon after that, we launched our very first satellites. So I'm going to ask here, does anybody know what the first U.S. satellite was? Does anyone? Usually, if I go to a grade school, okay, the kids always say Sputnik, which, you know, since the fall of the wall, I guess is kind of like that. That it's the same. So does anybody know? The United States was in a battle back then between the Army and the Navy. Okay, the Army's was using launched Explorer, and the Navy was launching Vanguard. All right, and even though the Navy was first to give it a try, all right, unfortunately there were some failures, and actually the first U.S. satellite was Explorer. However, the first first solar-powered satellite ever was Vanguard out of the Navy. And I have some historical clips, I think, here of the launching of this thing. Let's see. So that's the rocket, okay. Vanguard going up. Oh, I hate when that happens. So there goes the satellite down there. Now, if you want to see that, Vanguard satellite, you can go to the Smithsonian, okay, in Washington, and in fact, it's the one that they have on display that they were able to rescue from that very, very first launch, which was back. In fact, it's almost the 50th anniversary of the first failure of a U.S. satellite back in December of '06. So you always can get an anniversary for something like this. Well, I do have, I think, the successful launch of Vanguard.
After two much-publicized failures, Project Vanguard scores a bullseye on its third firing at Cape Canaveral. A grapefruit-sized satellite is set into the nose cone of a three-stage rocket, and the launching routine begins. The countdown goes with amazing ease, even faster than that of the Jupiter C. Only 16 seconds off a precision schedule, the Vanguard blasts off. It's one of the most perfect flights ever seen at the Missile Center, and there's not a hitch along the way, as the tiny moon is catapulted into the farthest orbit yet, 2,500 miles out. This launching was basically an experiment to test the rocket's flight pattern, preparatory to the launching of a 21-inch satellite later this year. Successful orbiting of a 6-inch moon was sheer profit as far as the engineers were concerned, making the first good news from Project Vanguard very good news indeed for all America.
So back in the 1950s, what happened was this first Sputnik went up. And this caused a real problem in the United States. People became terrified that the Russians, okay, the Soviets at that time, were so far ahead of the United States, not only in space, but it was reflected in science. And the good part of that was it caused a huge attention and a huge interest in science and technology and education, which brought a lot of people into this. My analogy here in this talk that I'm going to use is that I think we're at the same point right now in the United States. And that is, there's a huge, we'll talk about this, a huge need for clean energy. You know, we talk about global warming and everything, a lot of interest that is coming in this area. So I hope this whole thing that's happening, all the things we're seeing, will cause a huge interest so that now maybe, okay, a flux of science and engineering talent into renewable energy will be the analog of what happened into the 1950s for space. There's a huge need for this now, and a huge thing that people can actually tie their lives to for the future. That's not only is one that can do a whole lot for what our future has to be, but also one that you can make money on, okay, if you look at that side. So, by the way, they talked about the reliability of a solar satellite. This is the beep that came from Vanguard, okay, when it went up there. And what happened was, of course, when they launched the satellite, this little 6-inch sphere, okay, it's about the size of, if anyone who was here from Chicago, a 16-inch softball, all right, that's exactly what it was. They launched this thing, and the scientists, there's this group that broke off from Bell Labs, and they wanted solar on this satellite. But of course, the Navy scientists said, we have to have something that's reliable to put up there. Batteries. Okay, batteries so they negotiated, okay, and they let this group put on solar cells onto Vanguard and put it onto this whole thing. And in fact, after 2 weeks, the batteries ran out, and the thing switched over to the solar cells. And for the next 2.5 years, okay, the thing was powered by the photovoltaics. In fact, the only reason it stopped is the satellite's orbit kept increasing until it went through the Van Allen belt, and the radiation, okay, the people from the center here who study radiation and all that will know that this destroyed the electronics and everything. By the way, Vanguard, okay, is the oldest piece of space debris that we still have up there. It's still up there. Sputnik came down, Explorer came down, but Vanguard will be running, I think they said, for the next 60 years, okay, at least will be up in orbit there. So it's just a piece of space junk in case you go up there and bump into it. But it is our first solar-powered satellite, and as you know, okay, solar in space now is our primary thing for anything that's near Earth. And I tell people that if you don't think that solar is real, everybody here, okay, is benefits from solar right now. Every time you use your cell phone, every time you use your ATM machine, and every time you use your DirecTV, that information, okay, is transferred via those satellites, which are all powered by photovoltaics on this whole thing. So anyway, we'll look at those technologies in a little while. The people at Bell Labs were pretty smart, much smarter than us now, is that they knew also how to market things. And so when they held their first news conference to announce this huge breakthrough, as they call it, for energy in New York, in fact, they had more publicity about the solar cell than they did about the transistor at Bell Labs. They announced this thing, and they realized that people would have a hard time understanding this. So what they did is they made a little thing here, okay, out of an erector set, all right, which when they shine the light on, okay, the thing went around and said, Bell solar battery, powered by, I guess it's backwards, it's some other language. But anyway, they did this, and then when they put their hand in front of the Ferris wheel, it stopped, so that people got the idea that indeed, okay, the power was coming from these very, very small devices. Okay, and these were devices very, very much like this. And I'll pass this around, you can look at it. Very, very soon after this, a commercial company started up, and their first product, okay, was actually something for the consumers, making. Do you know what this is? Well, it's actually the original iPod. Okay, on the whole thing. So except it was powered by the sun. You can see there's a switch on the back because we didn't have rechargeable batteries at this time. This is from 1957. All right, so it's also 50 years old, all right, and the whole thing. So that it has and so that you switched it. If you were at the beach, you put it on solar and played the radio, and if you were at home, you put it on battery. You can look at this thing and see and now it's 50 years later, and this still works, except the switch is broken. And I tell people that it's kind of I'm a little bit older than this radio, and hell, I have parts of me that don't work anymore either. So if you want to pass this around and look at it and see this. So anyway, they did this, but they were very good at marketing this, and I think it's something that the renewables community can do a little bit better job at is marketing these things. By the way, if you have to go and leave and go somewhere, you can go ahead and get up and leave. It wouldn't be the first time that someone walked out while I was talking, so it's just fine. I see that I'm halfway through this talk now, so I have about another 20 minutes to a half an hour to get in here. But if you have to leave, that's fine, so don't worry about that. But let me play a couple things that have happened with renewables that I think are examples, and especially students should look at this. And the reason is that, for all of our lives, indeed, what we do is we market ourselves. And I don't care whether it's marketing yourself to get into Vanderbilt, whether it's coming in and marketing yourself to get into graduate school, or marketing yourself if you're a professor in order to publish a paper. It's part of this whole thing, of going through this process. Or whether it's a proposal, certainly if you send it into the Department of Energy, it's all part of this marketing to do this. And it's something that we haven't done very well with our renewable technologies until lately. And I'm going to play a couple of commercials for you that I think are examples of how marketing can change the direction and educate the public, which is very, very important in this case. So, and the first one has nothing to do with photovoltaics, but it's a technology that's out there, and it's one that's very economical if you have this resource. So.
Imagination at work.
This is kind of good. It has the message in it, and I think if people, the public, can look at this and get the idea, oh yeah, look at that wind is putting that boat ahead and everything, and indeed maybe it can be used for power. And it has this thing with a little humor in it so that you can associate it as well. Photovoltaics hasn't been quite as good, even though GE now owns a photovoltaic company, and I'm sure they must be working on their ad here, but I grabbed this one from Europe. Okay, it's a little bit of a promotion thing that they play on television, and this one came off of the UK from a photovoltaic company. Now I'm going to warn you, when you start off, okay, you start to see this. It's kind of like the attack of the batteries on this thing, and so it kind of looks like a horror picture. So it builds up at the end, but it does have a message. So. So this is one that's a little bit different. Okay, I was very impressed with everyone on here when everyone was getting hit by those batteries, almost killed, were laughing. Okay, this side of the room was a little more serious. That's good about the whole thing. So I don't know what exactly it means, but the psychology department can handle it. But you can see at the end, okay, it had a message in this whole thing. Okay, the fact that all this energy comes down and it's bad we don't use it. That is part of the thing that we're trying to do, is to use this energy source, the whole thing. So anyway, going back to what I'm going to talk about now in these last 20 minutes that we have here, is to get through and look at some of these technologies and where we're going and why we're going there. So it's based on Malcolm Gladwell's book, okay, The Tipping Point, which is that point where some event hits, okay, and it spreads like wildfire. And that's where this technology is now. If we do everything right, all right, it will become reality. But we have to see. So what is the issue? Okay, this is the challenge. And people who have heard many, many talks like this whole thing is that someplace here in 2007, I'm an electrical engineer. So if you take all the energy and put in electrical engineering terms of watts, we consume someplace like 14 terawatts of energy right now. By mid-century, all right, and that's if you take everything, transportation and convert it all into watts on this whole thing, all these fuel sources. By mid-century, this is going to about double on what we consume. This is a lot. And the question we ask is, where's this going to come from? Where are we going to get this additional 10 to 15 terawatts of energy? Okay, the electricity, fossil fuels, nuclear, renewables, other fuels, fossil sources. And of course, the answer is yes, because what we have is a portfolio of energy sources that we have to work with. And somehow we have to sort these out and use the best ones, okay, for the best circumstances, and look at what else is happening and make choices on these all things. If anybody thinks that all of a sudden we're going to switch over to photovoltaics and to solar, it's not there. It's going to take some while for this technology to prove itself and to build up capacity so it's part of our energy future. Will it be? Yes. But so will fossil fuels, so will nuclear, so will all these other sources as far as that. So remember that we don't have a problem with nuclear energy right now. We don't have a problem with renewable energy now. We have an energy problem. And if we're going to solve this, I think that all these people working in this have to work together. And that started now in order to come up with a solution, because we have some grave problems that are facing us. In fact, I think that's what I'm going to talk about now. If you look at this projections for all these terawatts we're going to have, this is what the Energy Information Agency says we will have in the future. Now, if you look on the renewable side, it looks pretty good, but you have to realize that they put hydro in there with renewables, and big hydro is a big part of that scheme. But what you can see is that oil, okay, they expect to go off a little bit, but this huge increase in coal as we're going on. And I'll point out again, okay, that photovoltaics doesn't compete with the oil really, okay. It complements the stuff that's going on in coal, all right? And 51% of the electricity in the United States is produced by coal, so over half of the electricity we have here. And the scare is this. So if you look at on the oil side, okay, if you're worried about global warming and all these things and hydrocarbons and all the CO2 and everything that goes up on this whole thing, if you look at the history of the car, this is what's happened in the United States since 1900 on the car, and how many cars we have essentially per person. So this is vehicles per 1,000 people. And right now in the United States we have about something of the order of 850 cars per 1,000 people. Now if you look at it per driver, licensed driver, that means we have about 1.3 or 1.4 cars per driver in the United States. It's pretty incredible. But if you look at the rest of the world, it's not so much. But if you look at where China is right now, it's way down here where we were in about 1913 or 1914. And that's a hugely growing economy. And the number of cars that are coming into China is going up incredibly. And one can think what's going to happen as they come up this curve themselves and what happens from the emissions from all those cars. So transportation is a huge part of this energy future. However, as I said, photovoltaics, okay, you have to look at some of these other competing things. Look at coal. And if you look at what's happened in the world, okay, here's some countries. Here's the United States, okay, and what we're doing, we consume quite a bit of coal. We probably have about 300 years of coal left, okay, so it's not a scarce commodity at all. But if we look at what's happening in India and China, especially in China, the amount of coal consumption is going up. In fact, right now, China is building or commissioning a coal-fired electrical plant every 5.12 days. This is, and you know those plants aren't as good as the ones in the United States, and the coal is not the same quality as the United States. And this is a problem. Now, people always ask, what happened here? Okay. Let me just answer that by saying that it's going to happen again out here when the Olympics start. It turned out that what China did this is when the Olympic Committee had the site visits in order to make a choice about where to go hold the Olympics in 2008. And so they're very smart. They cut down on the emissions. They closed the coal things. And as we all know now, about 3 weeks ago, they stopped. They went for the odd and even license numbers and they don't come inside the seventh ring or anything, okay, on alternate days. And I think 2 months before, they're going to stop all traffic, all private traffic coming in. They'll have to use public transportation. And then 1 month before, they're going to shut down the industry inside that area as well in order to make it so the marathoners can make it there without choking or something on the whole thing, which is good, but it still is a problem. The whole thing with coal, not for China and for us, okay, on this whole thing is this consumption. This is a world problem on this whole thing. It's a fast-growing economy there, and as I'll show you later on, it's also the one that is probably the third largest producer of photovoltaics in the world on this whole thing. Well, that's it. The solar power part of the solution, okay, and I'll answer it right now that at the end, the answer is going to be yes on the whole thing. But it's not going to come very quickly. Don't think it's just around the corner on the whole thing. Well, as I said here, it's at this tipping point that it's a real business right now. I said it's about $18 billion this past year worldwide, all right, so that it's grown very, very much. And an indication of this growth, I think, is shown here. This is typically one way they track this stuff over a function of time. And this last year, about 2.5 gigawatts of photovoltaic was produced in 2006. Of that, about maybe 2.2 gigawatts was sold into the market, or at least ended up in the market. So that it's starting to grow, and if you look at this year by year, the growth rates are rather substantial. If you go back over the last dozen years, the growth rates for the industry have been above 30% on this whole thing. And so the growth rates are high, but 2.5 gigawatts of power is not really a lot. Are there any wind people here? You know, it's a couple good wind machines, if you want to look at it that way now. Wind machines typically are I'm sorry, it's about, not a couple good, but it's about maybe 100 good wind machines. So this is not a whole lot. Or back in here, I remember when photovoltaics, I remember giving a talk in the UK where this was at about the 150 or 170 megawatt range. At that time, I went to the UK and gave a talk, and the guy right before me gave a talk on using some chicken manure factories. In fact, they had 3 of these chicken manure energy plants there that they collected this stuff. And it turned out at that time that they had 3 of these in operation, and they produced about twice as much energy, okay, as photovoltaics had done cumulatively up till then. And I had to get up there and tell them that I was kind of embarrassed that even chicken shit did better than this high technology on this whole thing. So why has this happened? Why has this growth happened for this technology? Well, it's not yet what has happened in the United States that it has done. It's happened because first of what's happened in Japan. And what Japan did, Japan was spurred on by some disasters, quite frankly. What happened was in the middle 1990s, they had the Kobe earthquakes, and then they had an accident at a nuclear plant. When the Kobe happened, they came in with their emergency vehicles, and they couldn't pump the gas because there was no electricity in the gas stations, so they had no way to power these things. So the first thing they did after Kobe is start to put photovoltaics on gas stations, so the electricity. But the Japanese were very, very smart. They saw the value in this electricity source. Of course, you know, Japan has no inherent energy. Okay? Even wind as an energy source is not very good for Japan. So they saw photovoltaics had a part of their economy, but more than this, they said, we'll help our industry, and they will become the world supplier of photovoltaics. So they will supply, and that's exactly what happened, because as we'll see in a little while, it's Sharp and Kyocera that are the leading companies. So they did this, and at first, okay, they provided an incentive. We call this in photovoltaics an incentive. Okay, really it's a subsidy, okay, but incentive sounds a whole lot better. So they paid at first half the price of the system, and as a function of time, the amount that they put in became less and less until 2005 out here. In fact, what happened is the incentive has gone away completely because the price of electricity in Japan is 22 or 23 cents a kilowatt hour, and photovoltaics competes with that. So it went away. However, the price of electricity here is not 22 or 23 cents a kilowatt hour on average. Okay, so we have to bring it down further. The big boost, though, came in Germany. And what the Germans did is they provided something. Of course, they were hit on by being green. Okay, part of the whole thing, worrying about the environment, all this stuff. And they said, okay, when they started their program, is that, okay, Kazmerski lives here in Frankfurt, okay, and he has a house, and we give him half the price for buying his PV panels for his house. How do we know we get any value out of that? You know, how do we know he doesn't slap them up there, take the money, and not give us any electricity? So what they put in something called a feed-in tariff. So what they did, instead of doing capital buy-down, they guaranteed a price for the electricity that the consumer produced. And so what they did is they said, okay, what we'll do is sign a contract with everyone who puts the photovoltaics out and feeds the electricity into the grid that they can meter. They meter this out, but we'll not only pay you, okay, what you pay for electricity, we'll pay you something in excess of that. And if you signed the contract last year, you got about 60 cents a kilowatt hour, about 4 times what you paid for it. And it didn't take long for the people to figure out they could actually make money on this. And they started even to rent space on their neighbors' roofs and put the photovoltaics up and everything and the whole thing. So it caused a huge growth in photovoltaics worldwide. And they not only did this, guaranteed this price, they guaranteed this for 20 years. And they provided a push in it, and they said, but if you do it next year, it's going to be 5% less we're going to pay you for this on this contract. And the year after, 5% less than that. So it pushed you to invest as soon as you can. And so this became the model for most of the programs in Europe. And if you see what's happening in Germany, Spain, Italy, Greece, okay, all these, and even France, it's based on this feed-in tariff. There are only a couple places in the United States that we have going with this whole thing. So the United States says, well, what can we do, the industry here, to catch up with this whole thing? And they said, well, maybe instead of weapons of mass destruction, we should invest in methods of mass production for our industry. Because if you look at this, the United States continues to lose market share against the rest of the world, against Japan and Europe. And even the rest of the world, when you combine them, okay, has sold more photovoltaics into the market than we have. So there's a look at the industry to turn this around. And in fact, the largest producer completely in the United States, okay, of photovoltaics, is just a couple states north of here, is First Solar, which is a thin film company. Not even silicon, not even the stuff made out of this. It's made out of cadmium telluride. And the growth of this company is rather incredible. And in fact, if you even compare here, you can see even China is producing more than the U.S. The largest U.S. installation of photovoltaics is being put in southern Colorado, put in by Sun Edison in conjunction with our utility Excel. And they're buying the solar cells from China because it's the only source that's available right now. Pretty incredible. But anyway, China is producing, as they're now the 1, 2, 3. Up here, they're the 4th largest producer in this chain of people. I think they're probably now at least 3, if not 2. But once again, all their product is being aimed at selling into the markets in Europe and the United States because that's where the money is for buying these technologies. So I'm going to run through this stuff now a little bit faster so that we can get into these technologies. So the U.S. industry came up with a roadmap with some goals by 2050 to have half the electricity supplied to buildings provided by photovoltaics. Okay, how you do this? Okay, you do this by an investment in policy, okay, on doing all this stuff in policy. But that alone won't do it because policy opens up markets. They open up guaranteed markets so you can build capacities. But you need R&D for 2 reasons. The first reason you need R&D is to bring down costs of a technology that is too high. So you need this investment in R&D for that. And secondly, you need the investment in R&D to guarantee the future technologies are ready when we need them. All right, so this is very, very big, is that we can't only invest in what we have out there now. You have to have a portfolio that you look at longer-term approaches to this as well. So the United States came up with this Solar America initiative that the administration announced 2 years ago, or a year ago, I guess, in in the State of the Union, okay, and provided some goals. And essentially the targets are that by 2015, okay, photovoltaics will become cost competitive in those three markets, the three major markets we have right now. The first two, it can be higher because that's on the customer side of the meter. It's what you pay, and I pay for electricity. This is on the generation side. This competes with the utilities. So this is the program in the U.S., okay, just started. And it is a program that looks at not only helping the current industry, but also stimulating incubators or startup companies with these technologies that we need to come into this. Fortunately, President Schwarzenegger in California at the same time had started his own California Solar Initiative, which for the installation side will meet about 40% of the goals for 2015 alone. So California will become just a huge contributor to the Solar America Initiative. But there are a number of states now that are a big part of this whole thing that are building, including New York, New Jersey, Pennsylvania, all have big problems here. They all have big programs in this to bring this technology in. Well, where should we make this investment? If you go back to the Japanese and look at this whole thing, and look, they document everything and look at their program. What happens is at the very beginning when photovoltaics came in there, the greatest part was the module, but over half of it was in what we call the balance of systems. All the other things that come in there, including structures and changing the DC current and voltage to AC and engineering and paying for people to put the stuff in and all this stuff. And as a function of time, these things all decreased relative to that, till now the biggest part of the cost of the system is the module, the electronic component in there that converts the energy to electricity. So this is an indicator that maybe if you want to cut the cost of the system, at least based on these Japanese figures, the ones in Europe says that this is about 70% of the cost of the system, that we need an investment to bring down the cost of that conversion technology. In the United States, though, we still have one problem here, okay, that they don't have there is the cost of labor here is a big part of the system, and something has to be done to address this installation part to bring down, to make it useful here. So what are our possibilities, okay, if we look at this whole thing? Well, the first one, okay, is what we have been working on, and it comes from this very technology here. This has been the bread and butter for photovoltaics, silicon. And if you look back to 1975, 1976, this has been following an evolutionary type development. Now, I'll show what that means in a little while. And what happens is that this is first generation photovoltaics. So this is what we have now. It's the major player. 93% of what is out there right now is made of stuff that comes from this. And if we look at this, okay, in this whole thing, this is what has happened with performances, okay, at least in the laboratory, that efficiencies have gone up, okay, to where they in the laboratory can convert about 1/4 of the sun's power into electricity. So 1/4 of that of the energy that's in those photons coming down is converted into useful electricity. If you look commercial, well, I'll show you commercially in a second on this whole thing. However, this won't get us there fast enough. In fact, if we look at this, as I said, back to 1976, it finally has been following this curve, okay, which is an 80% learning curve. And what this means is that every time you double the capacity, the price for that product drops by 20%. This is kind of typical for lots of products that we have out there follow this type of curve. It has been evolving slowly along this whole thing. And if we look at some of these technologies, what we have to do is really accelerate this somehow. And somehow we have to also go in and look at some of these beginning second generation photovoltaics like thin films and some other things on this whole thing to go to try to not only to break away from this, but actually if you really look since the middle 1990s, it has been following a 90% learning curve, meaning that it's been going down only 10%. So that that in this evolutionary approach, people have been trying to push back toward the 80% learning curve. This will not get us to those 2015 goals. We need something else, okay, in this whole thing. Somehow, we have to bring up the performance. If you look at what's been happening, the industry has been starting to do this. If you look at what we have out there, these are 3 technologies that are commercial, okay, that have reached 20%, okay, on the commercial line, have demonstrated efficiencies per cell of 20%. And I can go through all of these, but let me just focus on this one. This comes out from a place called SunPower, okay, which has headquarters in California and in Texas. And they've had a rather incredible look at this. And I have a little animation here of what their cell looks like. They have done an incredible amount of engineering. So they have taken all the contacts off the front. So there's no obscuration of the light at all. So every photon can make it into that semiconductor. They're putting all the contacts here at the back and have engineered this thing electronically and everything, so just like kind of like an integrated circuit. So they have interdigitated contacts, plus and minus, on the back of this thing, so that they can capture every photon that comes down, makes it into the semiconductor, and then every photon can create an electron-hole pair that can contribute to the current, as I showed you at the very, very beginning. This is a little costly, okay, but they have now solar cells, on average, coming off of their commercial line that are 22% that they're reporting right now. And they have reported the first 20% module. And a module is a collection of cells into the thing that we buy as a consumer on this whole thing. So the technology is coming along, but even this probably isn't. This attacks this higher performance, but still we have to look at cost and other features. This is also all this work with silicon and all these products that have all these markets that have been opening up have caused a real problem with supply. And so what we have is a shortage of silicon, actually. And the reason is, quite frankly, is that all of a sudden the microelectronics people have come back in. The business is going very, very well. And so they're coming and fighting for the same supply of silicon. Last year, photovoltaics consumed about a little bit more than half of the silicon in the world. If you told people this 15 years ago, they'd tell you crazy that this would ever happen. But it's caused the price of silicon to go up. You know, when this thing all started back here, the price of silicon was somewhere around $20 to $25 a kilogram. Now, if you went on the spot market and had to buy it, you'd pay over $200 a kilogram for the silicon. So people have entered into long-term contracts and all kind of other stuff on doing this. Well, the problem with this has had some benefits. It's made the industry look at itself and make things thinner and utilize it better and everything. It's also accelerated other technologies. And sometimes now I tell people that, you know, back in my early career, okay, I actually had the solution for the whole thing. And is it okay if I go just a little longer on this? Are you going to kick me off? If anybody, once again, wants to stop or ask a question, please do that. But, you know, when I first started at NREL, okay, I was just kind of an honest scientist then. And like Bridget, I did surface analysis. And so I had the very first laboratory that was operating there, and within a very short time, and everyone was quite proud of this thing. But of course, if you go and see any of these laboratories, they look the same. Okay, lots of stainless steel. The stuff looks like you can make popcorn in it or something, and probably. But anyway, at the same time, all this stuff was starting up with solar, and the laboratory director, Paul Rappaport, our first director, never much liked to have me talk to anybody, okay, in the laboratory, because especially to anyone from the press. But late one afternoon, he brought over a reporter from the Rocky Mountain News, and the reporter came in with Rappaport. Rappaport told me, he says, "Okay, he's here." He says, "I have to get back for this meeting with the Saudis," and he says, "Could you just tell him about these technologies and go through the stuff and just stick to that and the whole thing." And he wants to hear about our laboratory operations. So I did. I started to tell him how high-energy electrons hit the surface of these materials, and you get the Auger. Well, this guy closed his his notebook at that point. And I thought, well, he's not too much interested, but I kept going on. Finally, he said, hey, he says, how come your director said the Saudis are out here? And I saw my opportunity. I said, I says, there's Saudis are out here to talk about solar. He says, well, why solar? They have all that oil. I said, well, they're not dumb. I said, what happens is they know that in the future that the oil's going to run out and they'll need something else. So now he's opened up his notebook. He's copying down. So I got this guy. So I'm going on. And I said, yes. And he said, well, why solar? I says, not only solar, photovoltaics. And I picked up a solar cell like this, and I handed it to him. I says, this is what they're interested in. He says, yeah, why? I says, you know what that's made of? He said, no. I said, silicon. He said, yeah. I says, do you know where they get silicon? No. I said, sand. And I said, the Saudis have a lot of sand. Okay? And then I thought I'd add a little bit to it. I said, and they plan to sell it to us for $40 a barrel. So our visit ended, and I thought that I was pretty well off the hook, okay? The next morning I came up and picked up the Rocky Mountain News, and the first page there was the usual stuff you saw, gas, oil prices. And I thought, good. And so then walking back in the house, and I opened up the thing to pages 2 and 3, and there it was. Right up there in that corner. So I thought, well, maybe I'm still okay because they start off here with diminishing oil reserves. But then I saw here in the second, according to senior scientist Lawrence Kazmerski, on this whole thing. So this was the shortest time ever measured in our laboratory. And that was the time between I arrived at the laboratory that morning and I was called up to the director's office. So there is a thing, and be careful, A, of what you say, and B, who you say it to. Okay, and this whole thing. So remember this for the rest of your life on this whole thing. Don't get in this whole thing as I did. There is a thing in here, and especially for the chemists, you have to realize that there's more on that periodic table, right, than silicon, okay, and the whole thing. And it allows us a number of other approaches. And let's just look at this. And this brings us into disruptive technologies. If we're going to make these 2015 to 2020 goals on this whole thing, we need other approaches. And these are thin films, concentrators, organics, all these other things that we hear about. Even in silicon can be a disruptive approach. And what I mean on there is something that jumps off of this learning curve, okay, and has this huge growth for a while and then levels off after that. And there's an example of this. The integrated circuit in the 1960s did exactly this. It jumped off that learning curve on electronics and had a huge growth for this integration. And as a result, the cost came down considerably and the prices. It's the same thing. So you can do it with that or with thin films, and this is probably the approaches we're going to see in the near term on meeting these things. And it has to be one of these disruptive technologies to be able to jump off, including crystalline silicon, in which we have thinner wafers down to maybe 100 microns, much higher efficiencies on these things, which could also disrupt us on this. So silicon is part of it too, but so are our thin films. And these are our major thin films we have out there right now. And you can look at all of these things. This happens to be copper indium selenide. This is a product here. It's a flexible copper indium selenide thin film product that's out there. Copper indium selenide, okay, if you look at this, looks very, very complicated on this whole thing. And if you look at it, most of the time it's built up on a glass substrate. But if you go through the whole thing, okay, it's a complicated material, but one that's fairly forgiving when you make it. And it's fairly easy to make into a thin film. There's something now of the order of maybe 19 copper indium selenide companies out there worldwide working on this very, very material. So that it's a thin film. The active element here is about 2 to 3 microns thick. Okay. you can make it in all kind of ways. This one happens to be made on a flexible substrate. It happens to be made on stainless steel, and it's actually used right now by the troops in Iraq and Afghanistan for charging batteries. It's one of the big things that you can't throw those batteries in. It's all in there, so they use this. They just lay it out, okay, on sand and charge. It's very good militarily. It makes no noise. Okay, so and it's almost a zero thermal target as well. So it works, and it works well. Otherwise, the military, as you can see, this is in your summer Iraqi camouflage. Okay, and I'm worried that very soon we'll have it in our fall Iranian camouflage. But anyway. So you can pass this around and look at it. It works. It works well. And the other thing I was so surprised at seeing is that this particular, I bought this, okay, paid about $10 a watt. So it cost me a little less than, this is 48 watts, okay, on the whole thing. So it cost me about $450 or something like this. Well, I thought, I wonder what the military pays, because they must really get soaked. You know, I said, this is a lot more sophisticated than a toilet or anything like our toilet seat. Well, they pay about half that, okay, because of the volume that they actually buy. So in case anybody's interested, you can buy the same thing at REI or any of these suppliers. And if you're going camping and want to charge your cell phone, I mean, that's real camping, I suppose. If you have to charge your cell phone, you can do that. So the technology is there. Okay, it's complicated. And this is the champion cell in that area. Nearly 20% of the sun's energy is converted into electricity. There's another thin film that has taken over, and this is cadmium telluride. I'm just going to show you this very quickly. You can make 10% solar cells or greater by all kind of methods, okay? Lots of stuff in here for chemical engineers. And a lot of work has been done on providing different oxide materials, transparent conducting oxides for the top, a lot of engineering and everything else. This thing has, the best cell is about 16.5%. But the incredible part about this is this company, First Solar, has taken this. They can make a whole module in less than 2 minutes. From starting the module till the time it comes out, they can make these things incredibly fast. And this is part of bringing down the cost, okay? It's a very, very, very easy process in the whole thing. But I want to point out here is that what they are doing is they're starting off with a production now that they have that's about a little bit more than 100 megawatts. And in fact, I think I have let me just show this. That's right here in 2006. At the end of 2007, they're almost going to have 300 megawatts. By the end of next year, they're going to have more than Sharp. Okay, this is manufactured in the U.S., but they are expanding here into Malaysia on this whole thing. And by 2009, they're going to have almost a gigawatt of production themselves, annual production into this thing. This is a technology, when I talked about a disruptive technology, this is one that's taking off very, very quickly. And if you want to invest your money in your retirement, you might look at First Solar on this thing. The stock has gone out of this world. So let me just go ahead and page through and point out there's also work with concentrator cells. And so you can have some very, very expensive solar cells and use these concentrators that I kind of showed you in the first slides on this so that if you have a concentration of 1,000 times, you only need 1/1000th of the area of the material so that you can fold the cost into this very, very inexpensive concentrator. And in fact, now we have reached performances in this technology that are pretty incredible, reaching close to above 40%. And if we look at the structure of these are triple junction cells. And what I mean here is we take 3 solar cells and monolithically grow them on top of one another. The bottom cell is tuned to the red part of the spectrum. The top cell is to the blue part of the spectrum. And the middle cell to the yellow-green part of the spectrum. So in the same area, you encompass more of the solar spectrum. You match the current through the whole cell, and so you can get very, very high efficiencies. And in fact, the best efficiencies we have, this happens to be a lattice match case where every atom in that structure every material lines up so there are no defects at all at those interfaces or anything. The best cells have been in the upper 30s, and the champion cell in this is a metamorphic or lattice mismatch design that maybe you read about lately from SpectraLab based on this, and that has gone over 40%. So this technology, and they are actually introducing this 40% cell concept into their commercial concentrating systems now, and I think that the first ones we're going to see are going to be installed in Africa. So the technology is coming along quite well. By the way, it's the same technology that's used in all of our satellites out there right now, so that every satellite that goes up uses this type of thing. There are other approaches in this whole thing too. There are these dye sensitized cells, okay, that have come on here, and they have reached efficiencies up above 10%. And
I just want to say one more. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Exactly how do you mean?
There's a great future in plastics. Think about it. Will you think about it?
Yes, I will.
Enough said. That's a deal.
so those who can remember the graduate from a long time ago, okay, said he was really all thinking about photovoltaics. And in fact, this technology has been coming along for organics. And I like this because Vanderbilt is working on these cells, you know, on this whole thing. This is real, but I still remember back in those same days when I got in trouble over sand. I also got into spinach at this time, and this article actually appeared here, and this group from Japan had reported some rather incredible efficiencies, someplace in here as high as 30%, and the press picked this up. Well, of course, that wasn't a conversion efficiency. Okay, that was the quantum efficiency that they measured on these things, and they showed them those diagrams. They got mixed up, but I thought that this would be a beautiful technology for photovoltaics, because if your yields went down, you know, you could always eat the stuff, or who knows, maybe smoke it. But a couple years ago, as we know, that's maybe what's happening over there in that chem engineering building. The whole thing is that MIT and a number of other groups are working on this, and there's some rather serious stuff on this biomimetics and these organics rather in this whole thing. So don't ever close your doors on technologies too early. It's something that we did very, very, very much. And so on the organic side, we have all these things. Well, you know, beyond this, in this last part here, I want to point out that we should never close our doors on this next generation stuff as well, the stuff that has to do with revolutionary technologies. It's something that many funding agencies are focusing too near term on, and we should look at all these things that we see and hear about in the literature, and actually some work that has gone on here as well, looking at all these quantum dots and nanotechnologies and everything that are really okay, so that we can have technology ownerships for those technologies that we're going to see not in 2015 or 2020, but the ones that we're going to need in 2030, 2040, 2050, that unless we start to work on now, they're not going to be ready, okay, to be able to use. Now, there could be breakthroughs and everything else, but we have to make the investments now. That this investment in R&D has to be balanced over this whole thing, so that we look at all of these areas, and we don't only focus on the very near-term stuff, or even only focus on the near-term and kind of mid-term. This is very, very important for us to make these investments in science and technology right now. Otherwise, we won't have them and we won't own them on this next part. We've made lots of mistakes, okay, in doing this, and I can give examples in our own laboratory. In the early 1980s, okay, we lost funding, okay, and so what did we do is we dropped funding for a program in conducting polymer solar cells, conducting organics, and told that principal investigator that we couldn't support it anymore and took away the money, and that was Alan Heeger. And Alan Heeger, 20 years later, won a Nobel Prize for working on conducting polymers. And who knows if we kept going and telling him if we had supported him, he may have gotten it for photovoltaics. But we didn't stop there. We also had a program at the same time. We also had the program at the same time in what were dye concentrator cells, and these were essentially dyes that were kind of organic dyes that were used and would you'd shine the light on them and they would luminesce at one wavelength. And so then you'd put solar cells tuned to that wavelength around this thing and be able to get very, very high efficiencies. Well, we cut that one off too, and the guy working on this was a guy named Ahmed Zawel, who, after we left, his funding went away. He went off and started to use those dyes, and he got the Nobel Prize for femtosecond laser. So recently we cut off a program here at Vanderbilt. So I think this is really very, very good news for you. That nothing better could happen on this whole thing, that I see great things coming in the future on this whole thing. But let's not forget these next generation of photovoltaics. And these are the things that are really exciting. These are the things that jump off of this learning curve incredibly and can lead to incredible cost benefits because of this. And if you look at all these things, you can see there are lots of approaches here. Multiple quantum, multiple exciton generation devices on all these things, so that you can actually have efficiencies, that are 50, 60, 70% in the future. And that's why we have to invest in it. The promise of this technology is the risk is high, but the payoff is even higher than the risk. So it's something that has to be done. There's all these devices. I said I would show some quantum dots, so they're on there. So that this is stuff that is being done and is being pursued. But keep your eyes open. But don't think that you're going to see this stuff on your roof in 2012. But we have to invest in this. So we also have to do something about getting these things. We can't. If you take a photovoltaic technology now in the laboratory, or you look back at any of these curves on this whole thing, you find out that it takes about 12 to 15 years to get it from the laboratory bench to the consumer. Bell Labs, started their program in 1953. 1954, they had the demonstration. By the end of 1954, they had modules working out in the field. 1 year from concept to commercialization. We can't do that anymore for some reason. We have to concentrate on doing this to get this stuff from that research bench to the consumer faster if this technology is going to make it. Well, I was going to say something in here about hydrogen. Okay, but I think I'll skip over this if I can. So let me figure out how I do this. I think if I do this and just kind of finish this up at the end. There has to be a better way to do this when I do this, but let me just go ahead and go through here. None of these programs are very good at doing this. So the whole point here is that, if we look back, we kind of look back 50 years in history and looked ahead about 50 years as well, is that there are lots of ways that this is said, is that you learn a lot from history to point you in the right directions. And many people have said this in very, very many ways. However, I should say that in fact it's places like this and people like this that really have the knowledge and everything. And what we really should be saying that it's easier to grasp the future, okay, if you know what that future should look like. And so I think that's the hope we have, is that with the students, okay, and the faculty, but also in this whole next generation, that we're able to mold this energy future into what we know this energy future should be. So I'm going to end it here. Okay, I just have my finale coming up, okay, on this whole thing. I want to thank you very much for your patience, but let me go ahead and see if this works. Okay. So thank you. You know, go ahead. I know that I thank you for your patience. Go ahead, and if anybody has any questions, you could ask them or
There's a reception out in the atrium. We can go talk outside.
Great. That's where also the food is.
Yeah.
Good.